Hi, my name is Max Itson, and this is my second lab for Physics 2212. So, what are we going to be doing today? Well, like the previous lab, we will conduct an experiment to determine how much excess charge is present on a piece of tape. We're doing this to use a variety of physics laws and properties we learned from class to observe the transfer of charge on normal objects. However, this time, we're going to be treating the tape as a line of point charges instead of a singular point charge. So, this time, we're going to be able to compare the two methods and figure out the differences and similarities between the two. So here are some of the physics principles that we're going to be using today. We'll be using Newton's second law, where force equals mass times acceleration. This will help us find the force of gravity present on the tapes. We'll also be using the line of charge formula. So unlike last time where we did it as a single point charge, we're going to be using this formula from class because we're going to be treating it as a line. And when we use our glow script code, we are going to be treating like a number of point charges. So we'll use Coulomb's law for that, same as last time, where force equals the constant k times the two charges over the distance squared. To conduct this experiment, we are also going to have to assume a few things. For starters, we are going to ignore air resistance. It is a very small value and just very tedious to find, so we're going to ignore it altogether. We are also going to assume each U-tape was made with the same amount of charge. Both tapes are made in the exact same way, so they will have relatively similar values, but this is also going to get rid of one of the unknowns in our Coulomb's law equation. Instead of having a Q1 and Q2, we're just going to have a Q squared. For the experiment, we ripped two pieces of tape off another piece of tape to charge them up, and held them close to each other like this diagram on the right. For our data, we found that the length of the tape was 0.2 meters, the mass of the tape was 0.2 grams, and the distance between the charged tapes was 0.0045 meters. Now this is all the measurements we need to find the magnitude of the charge, but the one we don't know is the sign. Where they are both positive or negative, they would repel, so we need some other experiment to figure out the sign. So we rubbed a pin against my hair, and we knew that was negatively charged, so all we had to see was the reaction between the tape and the pin. And we found that there was a strong attraction, meaning that our tape was positively charged. After combining the different principles and deriving an equation, we got a charge of 9.91 times 10 to the negative 9th power of coulombs. We got this by setting out Newton's second law, and since there is no acceleration, the net force must be equal to 0. So the force of gravity must equal to the electric force, and then we plugged in our formula for the charged rod, giving us this nice equation here in the top right. Like every experiment, there are going to be some sources of error. For our source of error, they tied very heavily back to our assumptions. We ignored air resistance, which could have played a key part in finding the net force, charging the electric force to change. We also assumed that each tape had the same charge. It is very probable that they had different charges, but we were not going to be able to calculate both. However, we also believe that the charges were not evenly spread across the tape. The way that we ripped it off, or it just happened naturally, the charges could have been spread all over instead of being even like we assumed in our experiment. Now over to GlowScript. Here's some of the code we used to find the force and to find our model. The top is our electric field equation, which finds the electric field of a point charge, and the one below is our line charge formula. So instead of the equation we used earlier to find it, it just sums up a series of individual point charges on the tape. Now here's the other part of our code. This code calculates the electric force on the top tape due to the bottom tape, but instead of for a singular point charge, it does a series of point charge present on the tape, and this also is going to create the arrow of the net electric field due to the bottom tape. And here is our computational model for the experiment. As you can see, instead of having a singular point charge like last lab, we now have a series of point charges representing the length of the tape and all the charges on it. We also have a lot of arrows. The green arrows are each individual point charge's electric force, and the sum of that is equal to the white arrow, so the white arrow is going to be the sum of all the small electrical forces, and the yellow arrow is the force of gravity on the tape, which you can see is equal to the net electric force. We also had some questions we wanted to answer. The first one is, would you have modeled each of your tapes as a single point charge like in the previous lab? Well, luckily for us, we did just that. The one on the left is a single point charge. As you see, it's very simple, very easy to understand. And the one on the right is our new one. As you can see, we have a bunch of smaller arrows leading to our big sum arrow instead of just a one like it is on the left. Our next question is, why do these estimates differ? And which value is more likely to be closer to the real value and why? Well, these estimates differ because of the way we represented the charge. In the previous lab, we did it as a single point charge, allowing us to use Coulomb's law for the calculation. But this time, we represent the tape as a line of point charges, so we used a formula for the charge of a line to calculate. We believe that the line of point charges is going to be a lot more closer to the real value, as the tape is made up of a series of individual charges, not just a single point charge.